Good morning, my dear students. I'm extremely happy to meet you all once again for a video presentation like this. In this particular video presentation, we'll continue with some more concepts related to set theory of class 11 of CBSE. I'm planning to add more videos for class 11 also. Those who want to have automatic notification about the new videos being uploaded, please subscribe by clicking the subscribe button as well as the bell icon. As continuation of the previous video, we'll discuss some more points related to set theory. Okay, if all the elements in a set are listed out exactly, it is called the roster form. It is called in the roster form. Okay, example A is equal to 1, 2, 3. Okay, if instead of listing out the elements, okay, if we express the elements in a given set with a common property meant for the elements, okay, it is called set builder form. Okay, the corresponding set builder form here will be x such that x is a natural number, x is a natural number less than 4. It is first three natural numbers what we have listed out. If I list out all the elements in a given set, it is called a roster form. Okay, if I write it with the common property of elements given in the set, the given set, okay, and it is called the set builder form. Therefore, this is example of roster form. The same thing I have written in terms of set builder form. Set builder form. Okay, this is set builder form. Okay, I think if two sets AB are given and if have the same elements, they are said to be equal sets. Okay, for example, A has, let us say, 3, 4, 7, and let us say this is anyway cube root of 27, this is plus root of 16, and this is 49 by 7. Of course, you mean to say cube root of 27 is anyway 3, plus root 16 is anyway 4, and 49 by 7 is 7. They have the same element. Therefore, A and B here are equal. A, B here are equal. Okay. And one more thing I forgot to tell you even in the previous video. The order in which write the elements, it is immaterial. For example, if I am going to be given A, B, C as elements, it is the same as B, A, C. It is the same as CAB, therefore order doesn't matter. Okay, the way in which write the elements, it is immaterial. You can write the elements in any order, in any set. Every element is written only once, everybody knows that. Okay, if cardinalities are equal for two finite sets, okay, two finite sets A comma B, then we say that AB are equivalent sets denoted as A is equivalent to B. This symbol is called tilde. This is used for similarity of triangles. You might have seen in your classes. Okay, for example, let us say A has elements A, B, C, and of course B has elements 1, 2, 3, and of course n of A here is equal to n of B is equal to 3. Therefore, A, B, or this is an example of equivalent sets. Now we have two different application over here. I can give a statement and you can just verify whether it is true or not. Any pair of equal sets will be a pair of equivalent sets. Of course, it is true because if I am going to think about equal sets, all the elements are the same in both the sets. The number of elements will also be equal. Now, for any pair of equal sets will be automatically a pair of equivalent sets. For example, let us say C has 1, 2, 3, and of course D has 3, 1, 2. Only the order is changed, therefore C and D are equal, and n of C is also equal to n of D. Therefore, any pair of equal sets will be a pair of equivalent sets. But any pair of equivalent sets need not be a pair of equal sets. Okay, see here, A has ABC, B has 1, 2, 3. Number of elements are same, but they are not equal. Therefore, any pair of equivalent sets need not be a pair of equal sets, but any pair of equal sets will be definitely a pair of equivalent sets. Any pair of equivalent sets will be a pair of any pair of equal sets will be a pair of equivalent sets, but any pair of equivalent sets need not be a pair of equal sets. Equivalent sets need not be a pair of equal sets. The equal sets will be a pair of equivalent sets again. Okay, equivalent sets again. Next, just see here, if two sets A, B are given, then if all the elements are A are also there in B, I mean to say A is a subset of B. The symbol over here is written like this. Example is, just let us say A is equal to 1, 2. B has, let us say, 1, 2, 3. All the elements of A are there in B. Therefore, I mean to say A is a subset of B. Here, listen carefully. Both the elements 1 and 2 of A are there in B, but other than 1 and 2, there is one more element 3 which is in B, not in A. In such case, I mean to say A is a proper subset. This symbol is called proper subset. This symbol is called a proper subset. Okay, you may just think over they may be equal or also. Okay, you are not very sure. In such case, we use this particular symbol. Okay, I'll either use write proper subset like this, or we can write like this. Both are same for proper subset. Okay, and every set is considered to be a subset of itself. Okay, all the elements of A will be definitely there in A automatically. They have the same set of elements. Therefore, we come to the conclusion every set is a subset of itself. An empty set is considered to be a subset of every set. It is taken for granted. Empty set is considered to be a subset of every set. Okay, and if I am given a set A, and if I am going to write all the subsets of it, I take down and all the subsets of the given set. Okay, such a set is called power set, denoted as P of A. Power set. Okay, let me just think about this particular tabular column. A, what happens to N of A? Then P of A, what happens to N of P of A? Let us just check. Okay, let me take empty set. Okay, here it has number of elements 0. Here power set is, it contains empty set. It has one element. I can write it as 2 power 0. Okay, let me take the set containing simply A. There is only one element here. The subsets will be empty set and set containing A. Here it would be anyway, sorry. There are two elements here. This can be written as 2 power 1. Then let me take A comma B, two element set. There are two elements here. What are the subsets here? Empty set, then set containing A, set containing B, set containing A and B. Okay, there are four elements. I can write it as 2 square. And of course, you have A comma B comma C. There are three elements. What are the subsets here? Empty set, set containing A, set containing B, set containing C, set containing A and B, set containing B and C, set containing A, B, C, A and C, and finally set containing all the three elements A, B, C, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements. Therefore, you can have a generalization. If N of A is equal to M, M is finite, then N of P of A to B is equal to 2 power M. This is possible only when, of course, for infinite set, automatically it is infinite. It is understood anyway. Let me repeat. I took A as an empty set. Number of elements here is 0. Power set has set containing empty set. It is a singleton set. There is one element. I call it as 2 power 0. I have set containing only A. Number of elements 1. Power set. Power set is set of all subsets of the given set. Empty set and set containing A. There are two elements, can be written as 2 power 1. There are two elements A and B. Empty set, set containing A, set containing B, set containing both A and B. There are 4 elements, can be written as 2 square. There are 3 elements A, B, C. Empty set, set containing A, set containing B, set containing C, A and B, B and C, A and C. All the 3 elements. 1, 2, 3, 4, 5, 6, 7, 8. Can be written as 2 cube. Therefore, I have a generalization. If n of a is equal to m, where m is finite, then n of p of a is equal to 2 power m. Okay, this much you just remember. I think rest we'll discuss in the next video. Thank you students for patient watching.